Now we are splitting here this delta G in two parts. The plus is related to the forward reaction. Then we have the minus related to the backward reaction. So the overall delta G RDS is the plus minus delta G minus. Okay? Then we have wrote them. But now, in order to wrote them, we have to decide this part here, how we split it. We have to split in two. Okay? We have to split it in two. And we say, okay, let's split alpha time is over here in the delta G plus, and then alpha minus 1 is over here. So we are splitting this part in two. And this alpha will be a value between 0 and 1. Okay? It might be 0.5, and it depends. Okay? Now, once we have these two delta G, plus and minus, thanks to the transition state theory, we can write the reaction rate of the forward reaction, in which we have delta G plus, and the backward reaction, in which we have delta G minus. Okay? Then the overall, this is probably not clear to everybody, but now I make it more clear. The final reaction rate of our reaction will be R forward minus R backward. Okay? This is the total R. So we know that we are going from here to here. Why we know? We know from the beginning that from the thermodynamic point of view, this value is lower than this one. So we will have this reaction. It's just a matter of how fast, what is the rate, but we know that we'll go in that direction. Okay? Now, the rate we have is the forward minus the backward. That's the point. If we are good enough, we can have a very high forward and very small backward reaction. So we go very fast, very high rate. Okay? But we need a description. And this is what we are getting, a description. So we have an equation for the forward that will depend on delta G plus, and here it is. And then we have a description for the backward with delta G minus, and here it is. Okay? So now it's just a matter of putting this equation here, here, and this equation here, here. You say it's a hell. No, it's not a hell. We can simplify things. So this is what I'm doing in the next slide. Okay? Because at the end, I want to arrive to this one. Okay? Next. Here we go. I just reported these two. We have them here. Okay? To help. But what I've done is to put the delta G plus in the exponent of the forward reaction. Okay? Now the point is that the chemical potential, I zoom a little, the chemical potential of H2 can be written as the zero contribution minus, I will introduce here, minus 1/2 RT ln activity of H2. Do you agree?
Yeah.
So I am making explicit the dependency on the activity, because I want to have the activity evident. Okay? Same thing here for the H plus. So I put a 0 here, and then here I introduce a minus RT ln activity of H plus. Okay? Explicit, and make explicit the activity. Okay, now, when you put it here in the exponent, here I'm supposed to put all these value here, okay? All these terms. I put all of them, but the one with the logarithm and the activity. This one, because you have a logarithm over there, and here you have exponential, they will simplify, and you will have the activity over here. Okay? How? You see, you have here you have minus. You see here minus 1/2. For the property of the logarithm, I take this and put here as an exponent. You see that? It's an exponent now. Then you have RT. There is RT also over here. So it will cancel out with this one. So now you have the then there is a minus. Here we have a minus, so it will cancel out. So at the end, what you have is the exponential of the logarithm of the activity, exponent 1/2. So at the very end, here it is. The exponential of the logarithm. It's just a matter of making the calculation, okay? But just to show you where it comes from. This thing here comes from there. We have a logarithmic dependency of the activity. It turns out to be here, okay? Now, what we got, let me cancel. Okay. Now, and we got this equation, but this equation is ugly, okay? Exactly because here we have this chemical potential of the activated complex. What's that? We don't know. We don't know what's the activated complex, okay? And then this is a value, this is a fixed value, okay? But what we can assume is that this chemical potential of the activated complex can be assumed constant, changing, pay attention, the overpotential. Because we already introduced the effect of the overpotential over here in the alpha, okay? So we can assume that these two guys are constant when you change your electron potential. So when we change the electron potential and change our kinetics, these two will be fixed. So if they are fixed, I can introduce it inside our constant because it's a fixed number. They don't depend on the electron potential, and they don't depend on the concentration or activity of hydrogen. So these are the two things that are changing: electron potential and activity of hydrogen. They don't depend by neither of them. Okay? So I can introduce these two inside the K plus. So the K plus will become a K, a big capital KO. KO is the kinetic constant for the oxidation. Forward for us is an oxidation. So I call it O. Okay? So the exponential of these things here with a minus inside is introduced inside the kinetic constant. And now the equation we got is much easier. Much simple. So we are saying that the forward reaction has a certain rate, mole per second. Okay? And this rate depends on a certain kinetic constant that will depend on the catalyst, and will depend on the reaction itself. So this is experimental, no weights, okay? Or maybe with some very, very ab initio PFT modeling, very, very molecular-based modeling, you can get some indication. But in principle, you need experiment together. Then we have a certain dependency with an activity of the measured reactant. What is the reactant here? It's hydrogen for the forward reaction. To be honest, it's not hydrogen H2, it's H absorbed on the metal, but we know that it's equilibrium gas metal phase, okay? So it's okay, it's the activity of H2. And then we have a certain dependency, here it is, with, you see here we add Phi electrolyte minus Phi metal with a minus in front. Okay? So it's Phi met minus Phi electrolyte.
That is E.
And so we have with a minus in front, this becomes Phi met minus Phi
This one is
electrolyte.
fixed.
And what it is?
Yeah.
It is E plus, pay attention, V over potential. You remember this? 2 slides or 3 slides, more slides. Here we go. Here it is. Do you remember that from this one, we wrote that Phi met minus Phi electrolyte. When we are having reaction, we have E, HOR, plus ECA, the over potential, HOR. Okay? Okay.
Professor,
Yes.
if the mu star is constant, then why do we bother considering it in the first place? I mean, if we are
Not sit again, sit again.
so mu star, which you took into the constant k,
Yeah.
why do we bother it taking in the first place if it is assumed to be constant ultimately in order to reduce the equation?
Because if it varies, it means that K varies. So we want to know that K is constant. When you change, if you are changing A or your electron potential, you want to know that K is constant. And we are sure that K is constant. K will depend on temperature. K will depend on temperature because we have an intrinsic effect of temperature on K, Arrhenius style. Okay? Okay? And then also these two values will depend on temperature. Okay? So K will depend on temperature, but not on overpotential nor activity of hydrogen. So we got a simple equation here, okay? And what tells us this equation? That if we are changing, look at this, if you are increasing your electrode potential, we are increasing our rate. Is that coherent with the thermodynamic study? Yes, because this is an oxidation. So if we increase the electrode potential, we are pushing towards oxidation. Okay? So it's coherent. Then let's look at the backward reaction, exactly same way of reasoning. So also here we have 1 and 2. Also here, if you remember, we said we had minus RT ln A manage H plus. So this guy here, it was over here, but then I put it here. Once again, because we have the exponential of the logarithm and so on and blah 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 and ether were right there. Okay. Now these three guys this time, these three guys, activated complex, chemical potential 0 of the H plus, and chemical potential of the electron, they don't depend on the activity of H plus, they don't depend on the electrode potential. So I can bring them inside K as a constant value, and this value is now called capital KR reduction, because the backward reaction for us is a reduction. So that was oxidation, this is a reduction, okay? And what we got is this equation here, where pay attention here, because alpha is included between 0 and 1, okay? So it means that we have, this is the exponent here is positive. Here, alpha is between 0 and 1, we exclude the two extremes, and so it means that the exponent is negative. Okay? Do you agree with me? So we have so this one is negative. Let's select this, it's more clear. This thing here is negative. Alpha is positive. So, being this negative, what happened? If I increase, once again, our potential, if I increase, I have a minus, this is negative, so I'm decreasing the backward reaction. This is coherent once again. So if I increase my potential, I increase this, I am increasing this one, I am decreasing this one. Okay? So I'm making the oxidation more favorable. I'm helping the oxidation. Okay? While if I decrease the potential, if I decrease, okay, let's change the color just to emphasize that we are doing something else. I change the color. I decrease my electropotential. I decrease this one. I decrease this one. So what's happening? This is decreasing while this is increasing. So if I decrease the electron potential, I'm pushing the reduction.
Can I use this?
Okay? So everything is coherent with the thermodynamic study we have seen 2 slides ago. Okay? So we have the forward, we have the backward. Now it's just a matter of putting the two together. So let's go to the next slide. No, sorry, so I was forgetting these things here. This is very interesting. So, this is very interesting. The interesting point is that, so we have a kinetic description, but we want to be sure this kinetic description is coherent, consistent with the thermodynamic one. Okay? So, we can impose that the two reactions are equal, forward and backward are equal. So there is no overall reaction. And what happened? Do we get exactly the same electron potential from the Nernst law? We have a Nernst law that describes the equilibrium. Now we have the kinetics. But the kinetics, if I go to zero overall current, I get back the Nernst law. That's the point. If thermodynamic and kinetics equation we have are consistent, this is what we expect to have. And so what we do is to impose a specific condition. I put everything in blue to emphasize this a different condition in which we have equilibrium. So now you see that this level, the chemical potential, the electrochemical potential of H is exactly, so the product, the reactants, is exactly the same level of the product one. So it's equilibrium. Previous case, this was lower. Okay? So thermodynamic tell us that we go like this. Now is equilibrium. Is equilibrium, so they are exactly product and reactants, same level. So phi met minus phi electrolyte minus E, that is eta equal to the over potential eta, is equal to 0 now. Do you agree with me?
Yeah.
We are at equilibrium, so this is what's happening. So now let's write our two equations, the two we have just found, forward and backward rates, in the case we are studying. So the rate forward must be equal to the rate backward, and then over here in the exponent we don't have any more eta. Eta is 0, so we have just E. The value is E of the electric potential. Do you agree? Yes. Okay? So these two must be equal. And if we rearrange a little the two things and we make explicit E, so we have, okay, you can do by yourself, it's not so difficult. You are doing, you do by yourself, guys. Huh? You rearrange things, you put them together, you simplify the two alpha, and what you get is this one. So we know that E, equilibrium condition, from these two, is equal to RT over F, logarithm, the ratio of the K, the ratio of the activity. It's close to Nernst law, okay? So, but we know that Nernst law must be valid. Nernst law must be valid. So we have these two equations must be identical. So what we obtain is that, you see, you take this ratio of the 2K, you take it out, and what you got is a certain, and these two out should be equal to this term somehow, okay? Take them out, and what you obtain is that RTF ln KR over K0 must be equal to E0. This is what we got, if I'm not wrong, or too much wrong. Yes, it's right. Okay? This is a condition. A lot of scientists, engineers forget this condition. So your kinetics must be in agreement with the thermodynamics. Okay? So you got this. And from this one, you have a relation. Yeah, look at how I wrote it here, it's the same. So you have a ratio between KR and KO. So these are not independent values. They are dependent. So you make experiment and you get one or the other. They must be consistent. Okay? So when you have one, you have the other. And I remind you that E0 is E0 doesn't depend on the activity. So you are changing activity. The ratio should be the same. The ratio between the two K. Depends on the temperature. That's true. That's another stuff. Okay? So in this way, we are sure that thermodynamics theory we're using, Nernst law, is consistent with the kinetics we're using. Okay? So this demonstrates that what we are doing is somehow consistent. Huh? Then finally, we put the two together and then we are finished. I know the lesson is quite tough, but now we are very close to the end. Okay? Please resist. Fine. I know that it's tough today, but it's gonna give it a lot. No, also Wednesday will be quite tough, and then it's finished. The course is finished. Okay. Now, it's just a matter to put together the two. So we said we want to calculate finally what is the rate of our reaction. So we have just studied the rate of this reaction here, okay? And the overall reaction is, I told you, R oxidation minus R of the reduction. Okay? And here it is. Here it is. Then I want to have directly the current. I want to have the current. And what I know is that I am studying this rate determining step. You remember that we are studying from the H. And then for every single H, we have one electron. So this reaction rate is the one for H, not H2, H. We started from there. So every mole per second of H is reacting, we have 1 mole per second of electrons. So to go to the charge, we just put F. Okay? And now here they are. Forward reaction with just a F in front, and backward reaction with just F in front. So this is the equation from which we can describe the relation between I, the current, and here is the electrode potential. This is our kinetic description. It means that if we are able to change this potential, and you will see that we are able, we are changing the current. That's all. Okay? Now, of course, we have an effect of the activities, and we have an effect of the temperature. So we started from sketch today, and we arrived to a general, a description of the kinetics for our HOR. Now we can make it general, more general. To make it more general, we write this equation. I make it, I generalize it. And the general form is the so-called Butler-Volmer equation. And somehow we derived this Butler-Volmer equation here. So this is the kinetic description that is most used for electrochemical devices worldwide. So you can find people using more details, but it is not very common. Okay? Most of the people, most of the scientists, not people, engineers who works and develops components and technologies, they use this one. So we are not using a very simplified version because we are not able to understand. No, we are using the most used one. Okay? First. Second, most of the people who use this equation, they don't know where it comes from. Oh, really? So you can be proud to know where it comes from dynamics. And transition state here. Put the two together. I also reported here in small the thermodynamic requirements we have between Kr and K0. But I want to comment a little this general form. This general form, I just changed alpha into beta, just to make things a little more complex. So this distinction alpha and alpha minus 1 is generally very common and useful when you have RDS, rate determining step, where one electron is involved. If you have more than one electron is involved, things can be more complex. So this value I told you was included between 0 and 1, okay? And therefore also this one was included between 0 and 1. Now, when you go to reaction with more than one electron involved, things might be different. You can have higher values. Not only, not only. There are cases, for example, the ORR case
Okay, so if alpha is
that you are supposed to start in the homework. For example, the ORR case is much more complex. And then you have more than one electrochemical reaction. Just one is the RDS, but you have also other electrochemical reactions. So what's happening is that when you change the electrode potential, of course you are changing everything about this reaction, but you are also affecting somehow this group. So you cannot be sure that there is no influence on this. Okay? And this influence experimentally is observed, and it will turns out in introducing a different value of alpha. That's the point. Okay? So if we want to be very generic, include all the cases, we have to admit that our beta here can be greater than 1. Okay? They are always greater than 0, but they might be greater than 1. Okay? So I wrote function of redox steps, and the beta for the oxidation and minus beta for the reduction. So instead of putting alpha minus 1, I put it minus beta r. These two values must be greater than 0. I already put a minus in front of it, okay? But they don't necessarily be lower than 1. They might be greater than 1 in some equation, okay? That's all. Then here there is another critical point you have to pay attention. How to go from the reaction rate to the current. I told you in the case of hydrogen oxidation that we wrote everything starting from H. And so we put everything in that case, and we define the delta G in that case, and so on. And then, so the ratio here was 1. 1 electron, 1 H. Okay? There is a general way to calculate this value, and the general way, the general form is to calculate the number of electrons involved in the whole reaction, and then you divide by the number of times RDS occurs. For example, let's take our case of hydrogen oxidation. At the end, we have 2 electrons in the whole reaction. Okay? Because we have 2 times E minus. Okay? So it's 2 electrons. But we also have, so we have a 2 over here, but we also have 2 times the RDS. It means that each RDS gives you 1 electron. And so the equation is written for the RDS. So at the very end, we need to put the number of electrons involved in the RDS. Okay? That's all. Then, this equation here, I converted it introducing beta oxidation plus beta R. In the previous one, there was, over here, nothing. There was nothing. That was alpha minus alpha, in brackets, alpha minus 1. So it became 1. Okay? Here, we have this form. This is general form. And this is physically, theoretically consistent. Okay? That's all. So this is a very general form. So we have been able to derive it for a hydrogen oxidation reaction, and then we generalize it. So you can use this for every single electrochemical reaction you will find except there are some specific issues that require anything else. Now let's go more qualitative. Okay, relax a little. It's over. Okay? It's over. Bye. Relax. You survived. At least till I see. Yeah. Laid on the floor. What's going on? Now I would like to show you from the graphical point of view the Butler-Volmer equation. So the red one that is depicted here is the Butler-Volmer equation. So you are in equilibrium, you are here. Then if you increase, you are over here, so you have the value of the electrode is E. Then if you increase your electrode potential, so E plus eta is higher than E, you have a certain current, and this current, we say it's a positive current. Generally, the oxidation is considered the positive current. It's not a matter of choosing, okay? And so what you have is the red equation over here. Then instead, if you go below the value E, you see that you have a negative value of the current. It means that it's the opposite reaction. So you have a reduction. So in this case, in this domain here, where we have the oxidation, okay, the first term is prevailing. So this is very big. This is greater than this one. So we have oxidation. This is not clear? Can I say it again? So this is our equation. This is our Butler-Volmer equation, okay? So we have reaction forward, oxidation, reaction backward, reduction. This is a generic equation, okay? If I increase my electrode potential, you remember I'm increasing this. Here we have a plus in front, okay? So we are increasing the exponent, we are increasing all this. So this is increasing, okay? And this is the oxidation part, the forward is increasing. If I look at this one, here we have a minus, guys. So here we have a minus. So if I increase this one, all this term here is decreasing till here, okay? Is decreasing. Okay? If I increase the electrode potential, I am pushing the oxidation. Okay, I go here, I am in this, sorry, I don't move too much. I am increasing, I am going like this. You look, the current is going up. This is the oxidation current, it's a positive current, okay? While, change color, if I decrease this guy, I change the color once again because this always using the same, you can misunderstand. Here's the green. If I decrease this one, this is decreasing. I am decreasing this one, this is increasing. Okay? At a certain point, this guy here will be higher than this. And so the overall current will be negative. And here we go. We go here, below eta 0, so below E, and here it is, the current is negative. So we are going down, and this is the reduction part. So you see that we have just two quadrants. In this one, when eta is smaller than 0, we have the reduction. And here, red one. When eta is greater than 0, we have oxidation. Here, when eta is smaller than 0, we have the reduction. Okay? This is what exactly happened in a battery. In a battery, you look the for example, we are describing the negative electrode, for example. This is the negative electrode. When you increase the potential of the negative, you will have oxidation. So you are discharging the battery. If you increase the potential, decrease the potential, you are discharging. And this is the negative. So I am describing one single electrode. Then we have also the other one. Okay? So this is the description of one single electrode. Now, when you go to the extreme values, you see here, for example, the blue and the green are very similar. The blue and the red curve are very similar. And also here, the blue and the red are very similar. The blue curves you see are just a simplification of the Butler-Volmer equation. And the simplification that is done is that we are assuming when we are in the oxidation part with high current and high eta, high over potential, we are assuming that the backward is negligible. So when we are in the oxidation, we just take the oxidation. Okay? And so we call this the Tafel equation. Here it is. You say that here you are at very high current, very high eta in modulus. Okay? The Tafel equation is valid when the current I, in this case, is much greater than 0. And I am using just this one. Here it is. Then there is the opposite case, in which we simplify our Butler-Volmer, but in the opposite way. So we are saying we have a current that is much smaller than 0. Okay? Very low value. Okay? Very low value of current. So I am saying that this is negligible, this prevails. So I can describe everything just with this one, because the others become negligible. Tends to 0. Okay? So the Tafel equation for us is a simplification of the Butler-Volmer. From the historical point of view, it was obtained before the Tafel equation from experiments. And then, step by step, we arrived to a general description with a theoretical framework. Okay? Now, let's arrive finally to a device. It's just this device, right? Yeah. Let's arrive to a device. Do you remember our structure? We were something like this, negative and positive, okay? So in a real device, we have two electrodes. And if you remember, the negative, when we have a fuel cell or discharge configuration, we have the electron moving like this, H plus moving like this, and so here we have the HOR, so 2H plus 2E minus. Then on the positive we have the ORR, so we have 2H plus 2E minus plus 1/2 of 2 to give water. Okay? So here we have an oxidation, and here we have a reduction. Okay. Now let's look, this is the fuel cell case of discharge case, and here it is. So don't look at this one for a while. So let's look just at this part. And then here what we have is, this is the the negative electron. This is the negative one. Okay? You see we have minus all over. Okay? Then this value here is the equilibrium potential, E minus. E minus. Real case, when we draw a current, oxidation current, IO, the overpotential is positive. Of course, we said 100 times today, I increase the electrode potential, I push towards oxidation. Here it is. This is E minus plus eta minus. Okay? Now, let's look at, this is the negative. Then let's look at the positive one. Positive one. This is a reduction. So, we started from E plus. This is the theoretical value, the equilibrium value. Then, when we increase the current, we are going to lower value. So the electrode potential is decreased. So eta plus is negative once again. These things here is exactly, look at this, this is exactly what we observed here. It's a reduction. Okay? And what we observe here is exactly what we have here. Okay? But these times, these are two electrodes, two different electrodes. One is performing an oxidation, one is performing a reduction. Okay? Here we were looking at one single electrode and say, okay, you can do both of them. So these are two different electrodes. Something from, okay. So what's the overall curve we get? And we call it the polarization curve. The polarization curve is the real delta V we measure between the two electrodes. And this is the positive value. Okay, let's play. Sorry. Let's use the green one. Okay, let's take the positive value and we subtract the negative value. So this is the delta V. Positive potential minus negative. Okay? And here it is. So we have, oh, Siri, testo su Word, oh, Siri. Okay. So we have the positive one, so this one here, and we have to subtract to this one this, but there is a minus, subtract, okay? So the overall value, delta V, will have, during fuel cell or discharge mode, we have from the equilibrium value, that is E plus minus E minus, so when the two overpotentials are negligible, this is equilibrium, we have a distance, a deviation, and this deviation is exactly this due to over potential of the positive. Is that positive or negative? This is negative, okay? So we are moving down. And then we have another effect, a minus this effect. Minus eta minus, okay? That will give another negative effect. So this is the sum of this and this. So we have the two losses. We have two losses, one per each electron. Okay? Is that clear? This is negative. This is positive. But here we have a minus in front of it. So if I take with the minus, that becomes negative. Okay? So delta V is decreased from the equilibrium value by 2 factors. Over potential of the positive and over potential of the negative. So they are not compensating. They are summing up. There is a negative loss. Okay? So all this is valid in general. Pay attention that so far we are neglecting two things. One, ohmic losses. We already said it. Second things, we are neglecting another effect, that the activity of our reactant can be affected by the current itself. So the activity of hydrogen close to platinum, if you go to very high current density, it's decreasing because you have mass transport phenomena. Okay, so you have a gradient in the concentration in your electrode, and you have a decrease of the activity exactly on the active side. We studied that Wednesday. Okay, so we are making two assumptions: no ohmic loss. The activity of our reactants is not affected by the current. Okay. We will relax to these two hypotheses next class. So we are finishing just showing you what's happening when you recharge your battery or you have an electrolyzer. When you go to a negative current, negative means that you are having a reduction, overall a reduction, reduction current, in our case here. And what we got is that at the negative electrode, we are not having any more an oxidation, but we are having a reduction. So this time, eta is negative. Same thing, we are changing what's happening at the positive electrode. At the positive electrode now we have an oxidation, so eta plus is positive. So this is positive this time. This is negative, but then we have a minus in front, so it will become positive. So over here, so we have this, and we are summing up the two losses. So to charge our system, we need to provide a higher delta V, and then compared to equilibrium condition. Okay? In this case, we have an electrolyzer, so we are forcing in a certain direction our equation, our reaction, or we are charging the system. So we need to we need to give a higher delta E that is necessary. Okay? Because we are storing, we are forcing the equations. So we are converting somehow electrical energy into chemical energy. Okay? Is that clear? Final step, if you want, in some cases, you can use the Tafel equation. It's not easy to know if you can use it or not. For example, in a fuel cell, in a PEM fuel cell, polymer electrolyte fuel cell, you can use the Tafel equation for the ORR, the cathode, but you cannot for the hydrogen. Because hydrogen is very close to equilibrium, it's very fast. When it's very fast, it means that in the hydrogen you are here. It's a very fast reaction. And this current here is huge. This current here is huge. So you move a little, just a little from the equilibrium, and the current you obtain is huge. So you are close to the equilibrium. While just with few platinum. Okay? Then if you go to the cathode side, you put a lot of platinum, is another electrode, so it's another graph. Okay? Another graph, another electrode, you are here. This current here is the same value for the hydrogen to be here. So this current is the same as this one. Okay? It means that that current for the ORR is a huge current. Sorry, say it again. For the ORR, this current is far away from equilibrium, very far away from it. So to obtain this current, we need to have a very high overpotential, very high deviation from the equilibrium. To obtain the same current for the hydrogen, we need a very small deviation from equilibrium. Okay? It means that here we are far away from equilibrium, and it means that we can effectively use this one. So the oxidation reaction is totally negligible in a 10%. You will see that. So in some, you need to know the technology well to decide what to do. Okay? Otherwise, you need to study from the experiment what's the real overpotential. Then, anyway, in some cases, you can obtain, you can assume to use the Tafel slope. So I reported here the case of fuel cell assuming Tafel for both of them, for the positive and the negative, just to give you an overview. And in the case you have the Tafel assumption, you can, I told you, let's take the reduction here. So we assume that this is negligible, okay? So we can make explicit the overpotential or the potential as a function of current, okay? So what we are doing, here it is, okay? Writing not in a form of a exponential curve or relation, but like this. So we have E plus eta plus, and here it is the expression we get with the logarithm. Okay? Generally, in the literature, you'll find out many equations expressed like this. All the simplified models, they arrive to this one. And you will find often in the literature to call this guy here, RT over beta F, as a B. BR in this case, but it's a B, is the Tafel slope, and you see is if you draw this equation in the logarithm of the current, this is a logarithm. B is the slope of this equation. This is a line, because it's a logarithm. Here we have a logarithm of I. Okay? So B is the slope. And the so-called tassel slope, because if you report in a logarithmic scale, that's a line. Okay? And then you have here, generally these three terms are called exchange current density. And the exchange current density is the value you get. You can take it out from this logarithm. So it's a plus, you get a plus, no minus, blah, blah, blah. So it's a vertical translation. So it's a constant. Okay? Because you can take it out. So you will have a plus RT beta, we can call it B, directly. You will get plus RT, no, must scale, plus B R L N I star. Okay? So you can delete it from here and take it out. So this is a constant value. So changing I star, exchange current density, you are translating, shifting up and down your equation. Okay? So you can find in the literature written like this. Same thing for the other equation. You can find, not in tensor cell, but in other technology, you can find this expression. Okay? That's all. So what we've done today is okay? Okay? So there is a way to, in certain cases, you can simplify the Butler formula in the task. So you will find this. What's the matter, guys? There is something wrong with the sign. No, it's right. It's okay? Okay. Okay, guys, to wrap up. So we studied the kinetics, so now we have relation to describe how we have to change the over potential or the electrode potential in order to promote oxidation or reduction. So we have a thermodynamic interpretation, but we also have equations that we need to calibrate with experiment, but then we have a description. Next step, I told you, we'll need to deal with mass transport. Wednesday, then from Monday we start with the technology. So we start with PEM fuel cell, and I will describe the technology, and then we apply what we have seen to the PEM technology.